Hello and welcome to All Maths Considered. In this video I want to look at yet another problem which will help us to motivate graph theory. So imagine again we have a class of school children and some of them are friends with each other. Again, let us look at the numbers of friends for each child. So let's say each child writes the number of his friends on the card and presents this card. We already know from a different video that some of these numbers will be the same. Now let us ask ourselves a question: what about the parity of these numbers? Some of these numbers are odd, some of them are even. Can we have the situation where exactly one child has an odd number on his card and all others have an even number? The answer to this question is no. In fact, we can show that the number of cards with an odd number will be either 0, 2, 4, and so forth. In any case, the number of the cards with an odd number on them will be an even number. But how can we show that? So let us consider the following procedure. Let us say we ask children to take photographs with their friend. So each pair of friends, we ask them to take a common photograph, a joint photograph, print it in 2 copies, and then let each child sign his copy of this photograph. So there will be 2 photographs for each pair of friends. And of course, each child may appear in different photographs because he may have different friends. But let them sign their copy and put all of these photographs in a big sack. So in this sack you have all sorts of photographs of friends, 2 friends on each photo, and it is signed. Let us now count the number of photographs in the sack. Let us do it in 2 different ways. On one hand, let us go by the picture. So for each picture, there will be exactly 2 photographs, one for one friend and one for the other. So if we count like that, then the number of photographs in the sack is twice the number of friendships. We don't know what this number is, but we do know it is even. Let us now count in a different way. Let us count by the signature. So if we have a child and we count the photographs with his signature on it, the number of photographs like that will be exactly the number of his friends. 1 photograph for each friendship. So if we count like that, that is going to be the same as just the sum of numbers of friends for each child. So if we assume that each child wrote his number of friends on a little card in front of him, this is going to be just the sum of these numbers. So we have the sum of these numbers. We know it is an even number. Now, a little thought will tell us that if we just have a bunch of numbers and we sum them up and we get an even number, then the number of odd numbers in the sum is even, right? Because even, this plus even is even, and odd plus odd is even. So we need to have an even number of odd numbers in the sum. So, like this, we see that the number of children with an odd number of friends is even. It can be 1. It is always even. Now that we see it like that, let us repeat this argument, but in a formal way, using the language of graph theory and also using a combinatorial method of double counting.
So let us now consider this question in the formal setting of graphs. So remember that graphs were pictures like this, where we have dots and some edges connecting them. In our situation, the children are the dots, the vertices, and the edges are the friendships. For each vertex, if we draw all the edges and count their number, the number of edges is what's called the valency of this vertex V. We will simply write valency of V. Our statement then can be formulated as following theorem. So theorem says that in any graph G, the number of vertices with odd valencies is even. Let us prove this. Our proof will be by the combinatorial technique of double counting. Let us count the following pairs. So each pair will be a vertex and an edge, so that this edge contains a vertex. So count the pairs, vertex and an edge, where V is a vertex and E is an edge containing V. Let us denote this set by S. S is the set of such pairs. We have seen that the size of the set is 2 times the number of edges. So this is going to be denoting the number of edges, and this is because if we count by edges, if we count first by edge component, then we'll have 2 vertices connected to it. So for each edge we have 2 vertices, so each edge gives 2 elements in the set S. So the size of the set S is twice the number of edges. On the other hand, the size of the set, the cardinality of the set, is equal to the sum of the valencies of the vertices. So let's say we look at this sum, means we take all the vertices, so it's a sum over all vertices from the set of vertices, and we simply sum up all the valencies. This is because if we count this set by first counting the vertex component, so fixing the vertex component will give us exactly the number of edges which are adjacent, which contain this vertex. So that's going to be the valency of V, and we sum over all of them, and so we have this formula. So we obtain that this is an even number. But if the sum of all the valencies is an even number, then the number of vertices with an odd valency is even. So it follows, it's like this, it follows that the number of vertices with odd valency is even, which proves this theorem.